Hi, everyone. My name is Jianfeng-net, and I'm a PhD candidate from University of Southern California. In this talk, I'm going to introduce Quadrant, a cloud-deployable network function virtualization platform. This work is done in collaboration with Thomas, Georgine, Marcos, and my PhD advisors, Ramesh and Bharat. Today's networks are responsible for more than just forwarding packets. Network operators, such as enterprises, ISPs, and telecom companies, run all different types of network functions to process traffic. In the past, most network functions were implemented in hardware as meter boxes. Network function virtualization, or NFV, proposes to replace hardware meter boxes with software network functions running on commodity clouds. Operators can then benefit from reduced operational and management overheads of running a network. In NFV, traffic is processed by chains of network functions, where each network function is implemented in software. This slide shows an example of two network function chains. For traffic being processed by the second chain, each packet must be processed by a firewall first, and then by an intrusion detection system, and finally by an encryption network function. To achieve the original goal of NFV, both the research community and the industry are looking for solutions to make NFV deployable in today's cloud context. We believe that cloud deployability is quickly becoming a necessity for NFV. NFV must be able to support many network functions from third-party vendors to deploy them in today's commodity cloud infrastructure. In other words, we have to achieve performance, generality, and ease of deployment for NFV in a commodity cloud context. Here, we list out a few cloud deployable NFV requirements. First of all, as the network speed keeps increasing, NFV must achieve near line rate high throughput packet processing. For each network function chain, traffic volume can change dynamically over time. A cloud deployable NFV should be able to determine system resources allocated to each chain to meet latency objectives. The system must scale up and down each chain, target minimum packet losses, and a user-specified latency service level objective. Finally, as the NFV system must be able to support many network function chains with many network functions in it. Some of them may be developed by third-party vendors. In this multi-tenant cloud environment, it is critical to achieve memory and packet isolation among network functions. It means that each network function should have exclusive access to its internal states and packets being processed by it. So let's take a look at analysis on existing efforts on NFV. Among them, SNF proposes network functions as a service. SNF ignores many performance optimizations available in today's cloud and therefore has low performance. It also does not support chaining of multiple network functions. Metron is a highly optimized NFV platform. It achieves line rate processing for network function chains, but it requires source codes of network functions to compile them into a single process. This is impractical because network functions from third-party vendors are often released as closed source software. Compiling network functions into a single one also breaks the isolation requirement. NetBreaks also compiles network functions into a single process. It reduces Rust to solve the isolation problem. NetBreaks requires developers to write network functions in Rust, and also it still requires source codes of network functions. EdgeOS proposes a general NFV deployment that does not require a certain programming language. The key idea is to use a software switch to copy packets from one network function to the next one. EdgeOS sacrifices performance because of many expensive software-based packet switching and copying overheads in it. And different from them, in this work, we introduced Quadrant, which achieves generality and performance altogether. It supports chaining of multiple network functions from third-party vendors, and we do not use language-based memory isolation or copy packets between network functions. Quadrant supports SLO-aware autoscaling and can adjust system resources allocated to each chain to meet latency objectives. To achieve cloud deployability, we ask the following question in the paper. What changes do we have to make in order to adapt existing cloud infrastructure to support network function chaining, scaling, and isolation with high performance and generality? To do so, we make 3 contributions in the paper. First, we propose a high-performance spatial temporal packet isolation to avoid expensive software-based packet switching and copying overhead. Second, for high performance, Quadrant mimics run-to-completion scheduling to run network function chains and adjust the batch sizes for each network function chain to minimize the scheduling overhead. Third, Quadrant scheduling mechanism distributes traffic so that each chain's latency is within a target. Now, let's start with Quadrant high-level design. Quadrant deploys network functions as containers, and we develop on top of an open source fast platform. To manage our worker cluster, Quadrant reuses OpenFast worker management system, which based on Kubernetes. Each Quadrant worker runs many network function chain instances. For each chain instance, Quadrant dedicates a CPU core to it. Quadrant uses its own CPU scheduler to apply run-to-completion scheduling to network functions in the same chain. Our high performance comes from the spatial isolation mechanism. We call it spatial temporal packet isolation. Now, I will describe our isolation mechanism in details. We see network functions as standalone network applications, and for network functions' internal states, other network functions should not have access to it. However, for network functions in the same chain, they are processing the same set of packets in a sequence. Those network functions can share a memory region that hold packet structures to avoid copying packets for network functions in a chain. To achieve memory isolation for network function chains, Quadrant runs each network function in a container. Therefore, internal states of a network function are spatially isolated from each other. For network functions in the same chain, Quadrant allocates a shared memory to be used as the packet memory. Incoming packets will be placed in this shared packet memory for the chain. On Quadrant worker, there are many network function chains running. Each chain has its own packet memory. A new problem arises. So when traffic arrives at the NIC, how can it be split into different packet memory regions? A naive solution is to use a software switch to move packets. Quadrant cannot use it because it can incur significant packet switching overheads. Therefore, we use the NIC's hardware feature, SLO-adherence, to split a physical NIC into many virtualized NICs. Each NIC has its own packet memory to be used by a single network function chain. At the TOR layer, Quadrant determines a packet destination chain and modifies the packet's Ethernet destination address to match the virtualized NIC's Ethernet address. And then the NIC's L2 switch can forward the packet to the correct memory region. Now, packets have arrived at the shared packet memory region. How can we make sure that all network functions have unique access to the shared memory? We solve this problem by isolating network functions temporarily by using the cooperative scheduler. The key of providing memory isolation on top of shared memory is to grant exclusive access to the shared memory among network functions in the same chain. Unlike the default Linux scheduler, the cooperative scheduler runs network functions in a totally different way. Each network function runs without interruption until it finishes processing a batch of packets, and then it loses the access to the shared packet memory. After that, the cooperative scheduler wakes up the next network function, in this case NFB, and NFB starts to access the shared memory region and then process the batch of packets. Finally, the last network function C wakes up after all its predecessors finish processing. Now, FC is the only network function that have the unique access to the shared packet memory. After all network functions finish processing, the last network function also has to invoke the next function to transmit the current batch of packets. At this point, the NF chain finished processing without copying packets for each inter-NF hop. With the temporal isolation, Quadrant reduces expensive software-based packet copying operations. We also propose performance-aware scheduling and SLO-aware auto-scaling mechanisms. Due to the limited of time, I won't cover those in this talk. Please read our paper for more details. For evaluation in the paper, we include isolation and scaling performance comparisons and a detailed overhead analysis of different components in Quadrant. In the ablation study, we justify the design of Quadrant's isolation, ingress, and scaling mechanisms. In this talk, I will focus on the isolation performance. To study the isolation performance, we compare Quadrant NF isolation mechanism against other state-of-the-art network function isolation methods. To run experiments, we use Cloud Lab to deploy Quadrant in a cluster setting. All those servers are connected in a single LAN, connected through the switch. Traffic also enters the system through the switch. This figure shows the throughput of different isolation approaches at different network function chain lengths. The x-axis is the network function chain's length, and the y-axis is the per core throughput achieved by the network function virtualization system. As I mentioned before, NetBRICS achieves isolation by using a safe language, Rust, and EdgeOS sacrifice performance by copying packets with a software switch. Quadrant achieved the per core throughput that is up to 1.5 times higher than NetBRICS and 2.3 times higher than EdgeOS. We find that Quadrant's isolation performance is great. Our isolation mechanism is general to support third-party network functions. Next, we study Quadrant's scaling performance by hosting network function chains under dynamic traffic. We collect the time average CPU core usage of a system, and we compare our system with Metron, which is a highly optimized NFV platform that targets low latency but does not provide isolation. In this graph, the x-axis is achieved tail latency, and the y-axis is the CPU cores used by the system. First, we notice that Quadrant can adjust the number of cores to meet different service level objectives. However, Metron is not about to adjust core usage to target different latency. This shows that Quadrant is about to enable the trade-off between latency and efficiency for customers. We also find that Quadrant can achieve a smaller tail latency with a slightly more time average CPU cores compared to Metron. This overhead is reasonable because Quadrant, as we said, provides necessary inter-NF isolation for running network function chains. To summarize, Quadrant is the first cloud-deployable NFV platform that supports NF chaining, isolation, and scaling in cloud context without losing performance or generality. Quadrant proposes spatial temporal packet isolation, which is a lightweight inter-NF isolation mechanism for running third-party network functions. And we propose SLO-aware auto-scaling, which is able to adapt system resources allocated to each network function chain to meet latency objective. And our scaling algorithm uses less CPU core compared to alternatives when both providing isolation to network functions. Thank you.